Great. All right. Hi, everyone. Thank you all for being here. We're going to kick off with some quick intros. I'm Prithvi Okade. I'm currently a software engineer at Microsoft. I've been here for about 3 years now, just over. I work on Edge, the browser. Specifically, I work on commercial Copilot integrations into the browser. This is my second time at CppCon, so I'm very excited to be back. And I'm also very excited to be joined by Kathleen.
Hi, everyone. I'm Kathleen Baker. I also work at Microsoft on the Edge browser. Right now, I work on commercial features, and this is my first time at CppCon, so I'm very excited to be presenting today.
Great. Today, we're going to be talking about cutting down on unnecessary objects in C++. So as Kathleen and I both mentioned, we both work on Edge, which is a Chromium-based C++ project. And so as engineers, you all know, we give a lot of feedback, we get a lot of feedback, and over the years, we've noticed certain patterns where extra objects are created. This talk summarizes what these patterns are, gives a couple tips on how to detect these patterns, and then most importantly, talks about how we can go about correcting these patterns. Specifically, we'll be talking about basic strategies to avoid extra objects in string, vector, common STL types and containers, associative containers, and we'll talk about using transparent comparators and moving data to compile time for more improvements. Before we get into it, I just want to highlight that we have slide numbers in the top right of all of our slides. So if you have a question, we'll take it at the end. But if you could just jot down the slide number that it corresponds to, that'll be super helpful for us to refer back to at the end. Great. So I've been saying extra objects, unnecessary objects a bunch of times now. What do I actually mean by that? Let's start by considering this piece of code here. So we're initializing the string stir to be hello world, and then we're creating a copy of it in stir2, and then we go ahead and we print out stir2. So really all we're doing here is we're printing out hello world. And so instead, we could have just done this. We could have used cout, printed it out directly. We didn't actually need stir or stir2 to achieve this goal. The important thing to note here is that even with optimization flags, the second snippet here actually generates much less code. These two don't become equivalent. And so these two objects, stir and stir2, are objects that were unnecessary for us. And if we get rid of them, we can have some improvements here. Obviously, this is a very straightforward example. I'm literally initializing the problem here. I'm initializing stir and stir2. Moving forward, we'll talk about how this happens behind the scenes with methods that we use commonly. Okay, why are extra objects actually a problem? C++ is a value semantic language by default as opposed to a reference semantic language. So that means that on assignment, we copy the value, not just the pointer. So in a scenario like this, where we have an object of our type myClass, and then we create a copy of it, C and C1 are actually going to be different objects. And that's because on the second statement here, we're calling the copy constructor to create a brand new object. We're going to go into a couple of examples. Before we do that, I just want to highlight that we're overriding operator new and operator delete. We're just adding print statements so we know when they're being called. That way we know when objects are being created and destroyed in the following examples. First example is with string. So we initialize the string s to be this is a hello world string, and then we create a copy of it in s1. When we look at the printed output, we see that operator new gets called 2 times. And so what's happening in the second statement when we create s1 is the copy constructor is being called, and operator new is being called to allocate memory there. Ideally, we don't have this extra allocation of memory because allocating memory is a costly runtime operation. So if we can avoid that, that would be great. That brings us to using the move constructor. So here we are, again, with our string s, and then we create s1 using the move constructor. In the printed output, we see that operator new is only called 1 time. That's because the move constructor for string isn't allocating memory, it's just swapping memory. And so even though move is creating a new object, this is still a step up because it's not as costly for runtime. Ideally, though, we're not creating the new object at all. So that brings us to in-place construction. So here we have a function getStir. It returns our desired string. And then we set s to be the output of this function. When we look at the printed output, we see that operator new is only called once, just like before. So we're not doing the allocation of memory. We're not doing the costly runtime operation. And this is in-place construction. So no extra object is being created. And so in general, we're going to consider in-place construction to be better than moving, and moving to be preferable over copying. Next up, we're going to consider vector. So here we have a vector v with 6 elements in it. And then we create a copy of it in v1. We see here that we have two operator new calls. So vector's copy constructor is costly for runtime since it's allocating memory. If instead we use the move constructor, we only have one operator new call. The move constructor isn't allocating memory here. If we consider list, here we have a list with 3 elements in it, and then we create a copy in L1. When we look at the printed output, there's actually 3 operator new calls when we create L, one for each element, and then again 3 operator new calls when we create L1, when the copy constructor is called. So list copy constructor is even more expensive, and using move here is beneficial because we only get the 3 operator new calls when L is created and not again when L1 is created. So the move constructor here is better because it's not allocating that memory. So to summarize, extra objects are a problem because the object's creation can cause costly operations to occur at runtime. Costly operations are going to be things like memory allocation, which is what we were just looking at, making OS calls and running costly algorithms. It can cause more code to be executed at runtime. That's what we saw in that very first example with stir and stir2. And it can need more memory. It can need more stack or heap space at runtime. If you're wondering how much performance benefit you'll get if you do solve this problem, our recommendation is to measure your scenario because it can really vary based off of the code and the context that you're working in, as well as what you're optimizing for. We've been talking a lot about when extra objects are a problem. There are certain types where it's okay to create extra objects. Typically, these are for types that are smaller. So it's fine to create extra objects for plain old data types, like integers, floats, etc. And for objects that are considered small and do not do costly operations in their constructors. So things like string view, span, and dspan. Diving a little deeper into what we mean by small, as a rule of thumb, we can consider objects that the standard library considers to be lightweight to be small. So if you have a type that's less than or equal to 24 bytes in a 64-bit system and doesn't have any costly copy operations, we can consider that to be small. So something like string view or span is 16 bytes in a 64-bit system, and dspan is 24 bytes in a 64-bit system. And if you have a user-defined type that's meeting these guidelines, you're good to go. And then finally, before I hand it off to Kathleen, I mentioned at the beginning we want to give some tips on how to detect extra objects are being created. And so we have a list of compiler warnings and clang tidy checks that we can use. Right now, I just want to highlight wall, wextra, and weverything. In general, we recommend using wall and wextra because everything will probably catch too many problems. Throughout the presentation, we'll mention these warnings and we'll mention if they're included in wall or wextra or weverything. And with that, I'll hand it over.
Thank you. So now we'll look at some basic strategies to avoid creating temporary objects. We'll start with a non-trivial type as a read-only argument to a function. Here we have a function foo that takes string s by value, and foo is just reading s. This code calls foo. We're creating string s that's large enough to defeat small string optimization and then passing it into foo. We've also overridden operator new and delete again to see if a string is created when we call foo. Looking at the output, the call to foo prints operator new and delete, so it's allocating and freeing up memory when it's creating a string. In this case, it's better to use a const reference in the argument for foo. In the output, we can see no extra strings are getting created when we do this. As a rule of thumb, pass non-trivial read-only objects as a const reference in arguments to functions. Std string is a special case, and we can use string view instead. We'll take a look at string view later. It has some nuances as well. So we'll take a look at this same example again and see how we can use a clang tidy check, performance and necessary value param, to detect this case. This catches the issue and suggests making it a const reference instead. If we use a string view instead, this doesn't get flagged, so this is good to use. If we try making our own simple type, struct b, and create a function foo that takes b by value, this also does not get a warning. However, if we make a change to b and move the copy constructor out of line, this will get a warning. By moving the copy constructor out of line, b is no longer a trivially copy constructible type. The documentation for the clang tidy check says it only applies to types that are not trivially copyable or have a non-trivial copy constructor or destructor. Now we'll look at returning a non-trivial member object of a class. We'll create our own type, struct A. This will be our placeholder type throughout the presentation for non-trivial objects, and we'll be using it in examples. It has print statements and all its special member functions to help us understand whether copies are being made. So if the copy constructor is called, we'll see this printed. We'll try to improve on that by using a move instead. And even better is in-place construction without any copies or moves. Now let's use struct A in our first example about returning a non-trivial member object. We'll define a new class, my class, which has type A as a member variable and two functions, A, which returns a const reference, and A not great, which returns an object. This top code snippet uses A not great, and below is code that calls A. And here's the output for both functions, or both pieces of code. The copy constructor is getting called when we call A not great, but when we call A, which returns the const reference, no extra object is created. When returning a non-trivial member variable from a member function, return it as a const reference to avoid creating an extra object. Now looking at the same example with the more optimal function A that returns the const reference, here we'll hold the return type as a const reference, and in the second piece of code, we'll make a small change to hold the return type as an object. When the return type isn't held by reference, the copy constructor is called to create an extra object. Now we'll see if a clean tidy check can be used to flag this. We still have the same example with some minor changes. The highlighted code calls A without holding the return type by reference, and the second highlighted line creates a copy of object. When we use the clean tidy check, performance and necessary copy initialization, this flags both the issues in the highlighted code, where we should use a const auto reference and a const my class reference instead on the second line. Our next scenario we'll look at is using range-based for loops. We have this function getVec that returns a vector of n elements of our type A. This code calls getVec to create a vector of 2 elements, and we have 3 range-based for loops, the first one using const auto, the second using const auto reference, and the third using a forwarding reference. We can see in the output, the const auto loop creates 2 extra objects, but the other 2 loops don't create any extra objects. So it's better to use const auto reference or a forwarding reference in range-based for loops for non-trivial objects. When we use the warning range loop construct with the same code, we get an error about using const auto in the loop, so it's a good warning to use. Let's look a bit more into the range loop construct warning and see if it can catch all the issues we'd expect it to. Here we have struct A with one const member function foo and another non-const member function bar. In this code, we're creating a vector of strings and then using a range-based for loop using auto, and then we create another vector of type A and run 2 range-based for loops, the first using const auto calling foo, the second using auto calling bar. When the range loop construct warning is used, it just flags one of these cases, the const auto loop with the vector of A. When we use the clean tidy check, performance for range copy, it flags both the loop with the vector of strings and again the loop using const auto for the vector of type A. It doesn't flag the third loop that calls bar because bar is a non-const member function. Now I'll hand it off to Prithvi for the next section.
All right. Thanks, Kathleen. Okay, so we're going to kick off the next section by talking about structured bindings. Structured bindings allow for the decomposition of composite objects, so think things like tuples, structs, arrays. In our situation, we're going to be looking at a struct. Here we have a struct B. It holds an object of type A as well as an integer I. Here's 2 ways that we can use structured binding to gain access to that object of type A within B. The difference between the 2 is that the first one uses const auto, whereas the second one uses const auto ref. When we look at the printed output, we see that when we're using const auto, the copy constructor gets called, but when we're using const auto ref, we get no copy or move calls. And so because of this, we recommend using const ref for read-only structured binding variables. Next up, we're going to talk explicitly moving objects out of functions. So here we have 2 implementations of our function foo. They both create this object of type A and then return it. The first one returns it with an explicit move, and the second one just returns it directly. When we look at the printed outputs, we see that the first one calls the move constructor. This makes sense. We're explicitly calling move, so we expect the move constructor to be called. But the second one doesn't have any move constructor calls or copy constructor calls. Does anyone have any ideas as to why that might be the case? Yeah, a bunch of people are saying it. It's NRVO. So this is named return optimization, or NRVO, which returns to the optimization where named objects are returned by value from a function, and they can be constructed directly in the memory location of the caller's variable, which allows us to avoid this move or copy from happening. So what's happening in the first implementation of foo here is that this explicit move is actually preventing this optimization from taking place. So we don't want to use move in these cases. NRVO is not required by standard, but at this point, most compilers do implement it for such scenarios. Ideally, though, we use something that's guaranteed. And so that brings us to our third implementation of foo here that just returns this object of type A directly. This actually also doesn't result in any move constructor calls or copy constructor calls because of guaranteed copy elision from C++17. And so the compiler essentially knows to avoid unnecessary copying or moving of the objects. Copy elision is also known as deferred temporary materialization or unmaterialized value passing. If you're wondering how you're supposed to know that your explicit move is preventing this optimization from taking place, we have a warning that you can use, W pessimizing move. It's included in W all, and it lets you know that, hey, moving a local object in a return statement is actually preventing copy elision from taking place. In this scenario, for explicitly moving on return, we're actually going to want to move on return. So we have two implementations of our function foo. They both create this object of type B, and then use structured binding to gain access to that object of type A within, and then they go ahead and they return it. The first one returns it directly, the second one explicitly calls move on return, and what we see in the printed output is that the first one calls the copy constructor, whereas the second one just calls the move constructor. And so our recommendation is for non-trivial types in your return type, use this explicit move. This advice isn't just for structured binding, it applies in general to returning a member value from a local object from a function. So in our next example here, we're doing exactly that. We have our object of type B, and then we go ahead and return b.a. The first one does that directly, the second one returns it with that explicit move, and we see the same result. The first one calls the copy constructor, the second one calls the move constructor. So the same advice from before applies in this scenario as well. That explicit move allows us to have an improvement here. Okay, next up, we're going to move on to Lambda captures. So here we have a function where we create this object of type A, then we create a Lambda that captures A by value, and then we create a copy of that Lambda, fn2. Our second implementation here does essentially the same thing. It creates that object of type A, creates a Lambda, creates that copy of the Lambda, but rather than capturing A by value, it's capturing A by reference. And what we see in the printed output is that the copy constructor gets called twice in the first example. It gets called once when we create that first Lambda, capturing by value, and then again when we create a copy of that Lambda. In the second one, where we're capturing by reference, we don't get any calls to the copy constructor. So our recommendation is to use capture by reference when it's safe, so you can avoid the copy. Diving a little bit deeper into Lambda captures, we're going to modify the struct A that we've been working with. We're going to add 4 member functions to it. They all capture to create lambdas. The first one captures by star this, the second by this, the third captures by reference, and the fourth captures by equality. When we go ahead and we call these functions to get the lambdas that they return and then call those lambdas in turn, we see this in the printed output. The notable thing here is that when we use star this, we actually get a call to the copy constructor. So we recommend only using star this when you need it because it will make a copy of the object. A quick note about this example is that we're just printing out hard-coded strings, right? We're not actually using the captured member variable. So if we were to modify this example a little bit and print out A as part of the string, we would actually run into this error that says implicit capture of this with the capture default of equals is deprecated. That's because capturing by equality was deprecated in C++20. So if you're using C++20 or onwards, don't capture by equality. And then the last thing we want to touch on with Lambda captures is what to do if you have a variable number of arguments. So here we have 5 implementations of our function foo. It creates this Lambda that captures variable number of arguments, and then it calls that Lambda. When we call our functions, we see this printed output. The notable thing here is that the second 2 functions, the second 2 implementations of foo, are capturing the variadic arguments by reference, and those are the only 2 that aren't resulting in a copy constructor call. And so our recommendation when you're using variadic arguments is to use reference capture. And that will remove the extra copies. And with that, I'll hand it back to Kathleen.
Thank you. So now we'll take a look at some strategies for reducing temporary objects when using string and vector. We can use string view to stop creating strings at runtime. We have a function foo that takes a string by reference, and another function foo better that takes a string view argument. In this code, we create a string stir, which is created at runtime. We pass the string hello to foo, and it creates a temporary string. Each time we call foo better, though, no temporary string is created. And here's the output. String view can handle string, const star, and const star with length arguments without needing to create different functions to handle each one. It also doesn't do any heap allocation. String view can also be used to create the string at compile time instead of runtime. However, in some cases, we can't use string view. If we have a function like foo platform here that expects a null terminated string, we can't pass the string as a string view because string view may not be null terminated. There's no C++ standard null terminated string view. Chromium has its own implementation of a null terminated string view type that could be used in this case. If you want to learn more about string view, you can check out this presentation by Jasmine Lopez and Prithvi from CppCon last year. Let's look at an example where we have struct A, and it takes ownership of the string passed into its constructor or passed into the function setStir. So these are sync scenarios. Instead of using string view here, we can follow the C++ core guideline for will move from parameters, pass by rvalue reference, and move the parameter. So now we've updated the code to follow this guideline. Looking at the same code again without the updates, we can use the clang tidy check, modernize pass by value, to detect the same case and improve the code to pass by value and use move. Right now, this check only identifies this case in constructors. It's better to follow the C++ core guidelines from the previous slide to pass by rvalue reference and use move, but the clang tidy check suggestion is still an improvement. Our next scenario we'll look at is using an alternative to string operator plus. We have 3 strings we're concatenating using the plus operator. You can see 2 temporary strings are getting created, and then a final 3rd string is created. So in all, 3 strings are allocated memory. What if we can concatenate strings more efficiently? Here we have the same 3 strings to concatenate, but instead of using plus, we're using a function called mystrcat. You can see now only 1 string is created instead of 3 strings from the previous example. Does anyone have any guesses about how mystrcat could be implemented? Sorry? String stream? No, we're using reserve. So this is our definition of mystrcat. We're using reserve to ensure there's only a single allocation of the string before we concatenate it. Our definition of mystrcat is inspired by the absol_strcat implementation. And Chromium also has its own implementation called strcat. Now we'll take a look at small strings. If a string is small enough, no memory is allocated on the heap because string data can be contained by the string object itself. Temporary strings are still created though. In this code, there are 3 small strings being concatenated using the plus operator. No strings are allocated or deleted, but temporary strings are still created. If we use mystrcat instead, no strings are allocated, and we're only creating the 1 string. mystrcat is still optimal in this case because it's only creating 1 string. Plus is only optimal in the case where there's a single concatenation and either one of the parameters is a string. Now we'll look at how to use string view substr to remove possible memory allocation. We have a function remove scheme, which takes a const string reference, and another function remove scheme better, which takes a string view. Both of these functions return a substring using s.substr. And this code calls both remove scheme and remove scheme better. We can see when we call remove scheme with the const string reference, a string is allocated, but when calling remove scheme better with the string view, no extra string is allocated. If we don't intend to modify the result of substr, we can use string view substr to avoid extra memory allocation. We just need to make sure when string view is used, the underlying string memory is valid. So we used reserve to prevent extra objects when concatenating strings, and now let's see how reserve can help with vectors as well. In main, we're creating a vector of size 4. We use a for loop to emplace back 4 objects of type A. Operator new is called 3 times, first with size 4, then size 8, and then size 16 to resize the vector to hold the objects we're adding. The move constructor for each object is also called every time the vector is resized to move the objects into it. Let's compare to an example where we reserve the size of the vector before emplacing back objects. As you might expect, when we use reserve, operator new is only called once with the size of the vector needed, And the move constructor for A isn't called at all because no objects need to be moved. Reserve ensures there's a single allocation and no resizing is needed. There's a clean tidy check you can use to catch this in your code. If you have emplace back in a loop, it will suggest you call reserve before the loop. We can also use span to prevent vector creation. Here we have two functions, foo and foo better. Foo takes a const vector reference, and foo better takes a span. In this code, we create a C-style array and pass it into foo and foo better. Passing the C-style array into foo forces us to create a vector. In the output, we can see calling foo created 3 temporary objects, foo better created 0 temporary objects. So span allows functions to be used with C-style arrays without needing to create vectors. Using span also allows the function to work with other contiguous containers, like vectors, arrays, and initializer lists. One thing to note is initializing the vector like this with the initializer list creates extra objects. Prithvi will go over this case in some later slides. If we need a non-temporary object to be created, like in this case, we update A prior to calling pushback, it's better to use move. In the non-move example, the copy constructor is called, but when we use move, the move constructor is called. So it's better to use move to take ownership of the resources. And then I'll pass it back to Prithvi.
Thank you. Okay, this next section is on temporary objects and common standard library types and containers. We're going to start by talking about initializer lists. This is the example that Kathleen alluded to a couple slides ago. Here we're using the initializer list constructor to create this vector with 3 elements of type A within it. In the printed output, we see that these 3 objects of type A are created and then copied over into our vector. Instead, if we use reserve to allocate the memory that we need for our vector, and then in a loop use emplace back to add these 3 elements to our vector, this gives us in-place construction. We no longer have those copy or move calls happening. So our recommendation is to use reserve and emplace back to remove the need for temporary objects in a scenario like this. Next up, we're going to talk about pair. So here we have a pair with 2 objects of type A within it. We see those 2 objects of type A get created and then copied over into the pair. This first example up there is actually from C++20, which is what Ed uses. In C++23, this actually ensures move construction instead of copy construction. Before C++23, you could get move construction using make pair or by using the CTAD version of pair. Of course, ideally, we get in-place construction. And so to do that, we need to use piecewise construct for pairs. This is what it looks like to use piecewise construct for a pair. A little wordy, a little more typing, but it does give us that in-place construction. Tuple is pretty similar to pair. Here we have a tuple with 2 objects of type A in it. We see those 2 objects of type A get created and then copied over into our tuple. If instead we use make tuple, kind of like make pair, this is going to give us move construction instead of copy construction. And then also, like the CTAD version for pair, the CTAD version for tuple is also going to give us move construction. Of course, ideally, we get in-place construction, but unfortunately for tuple, there is no in-place construction, so move instead of copy is the best that we can do. If you're curious as to why this is the case, why there's no piecewise construct for tuples, we've linked a Stack Overflow post for, where you can look at the discussion once we link the slides. All right, in this next section, we're going to talk about optional. Here we're creating an optional of type A. We see here that that object of type A gets created and then moved into our optional. If instead we use make optional or the in-place constructor of optional, both of these are going to give us in-place construction. Actually, behind the scenes, make optional is using the in-place constructor of optional, which is why these both have the same behavior. So our recommendation is to use one of the 2. In this case, we're setting the optional value directly when initializing it. If instead we wanted to defer that creation, we could have an example like this. Here we initialize the optional to be empty and then later add a value to it. And we see once again that that object gets created and then moved into our optional. If instead we use emplace, that's going to give us in-place construction. So emplace is better for assignment in these scenarios. A quick note about emplace. If you have a scenario like this where your optional is holding a value and then you want to use emplace to set it to a new value, emplace is actually going to destroy the current object before doing in-place construction for the next one. So here we see that that first object gets created and then deleted before the second one gets created. Okay, next up we're going to talk about expected. Here we have a function foo that is returning a suit expected with the success type of A. we see this object of type A get created and then moved into our expected. If instead we use the in-place constructor of expected, that will give us in-place construction. So we recommend doing this instead for non-trivial types in student expected success type. Next up, if we consider the error type of expected, we're going to start by creating a struct error. This is very similar to the struct A that we've been working with in that it also prints in all of its special member functions. The first way that we can use, the first way that we can create an unexpected is like this, where we create the unexpected object and then return it from our function. This is going to result in us getting two moves. One when we create that unexpected object, and then another one because the return type of this function is an expected. If instead we use the in-place constructor of unexpected, this is going to give us one move. We no longer get that move when we create the unexpected object, but the return type still doesn't match. It's an expected. So we get one move there. And then finally, if instead we use the unexpect constructor of expected, that will give us in-place construction. We won't get any move calls. That's because now we're creating the expected in place and the return type is matching the type of the object we just created. So for non-trivial types being used in the error type of student expected, we recommend using the unexpect constructor of expected. Tongue twister. Okay, this next section is going to be variant. So here we're creating a variant of type A. Once again, that object gets created and then moved into our variant. If instead we use in-place type or in-place index, that will give us in-place construction. So we recommend using one of the two for non-trivial types being used in variant. In this case, we're just creating the variant. If instead we wanted to change the value type, we would have a scenario like this. Here we create our variant b. This actually initializes it to be an integer that holds the value 0. And then later down the line, we want to change it to instead be an object of type A. What we see here is, once again, this object of type A gets created and then moved into our variant. If instead we use emplace, that gives us in-place construction. So emplace is better for when you're changing types of a variant, when the type is a non-trivial type. If instead we wanted to change the value but keep the type the same, we would have a scenario like this. Here we initialize our variant b to be an object of type A, and then down the line we want to change it to a different object of type A. We see here that we get that extra operation. If instead we use emplace, we no longer have that operation, so this is an improvement here. So emplace is performing better assignment in this non-type changing scenario as well as the previous slide's type changing scenario. Another quick note about emplace, much like optional, emplace is going to cause the destructor of the current object contained inside variant before doing in-place construction for the new object. Okay, this next slide is on toArray. So here we're using toArray to create an array that holds two objects of type A in it. Those two objects are created and then moved into our array. Visually though, this looks nice. You don't have to specify the length, you don't have to specify like the type of the element every single time you add an element to it. But if we do use the array constructor directly, like so, where you do have to specify the length and you do have to write A before each of the elements, this actually does give us in-place construction. If you use the deduction guide, you get some of those niceties back. You don't have to specify the length anymore. But in general, we recommend when you have non-trivial objects in your array, consider using the array constructor rather than using toArray. And then finally, before I hand it back to Kathleen, we're going to talk about adding elements to vectors and other iterative containers. So we're going to make one modification to our struct A. We're going to add this member variable at the bottom, and then we're going to print out the value of that member variable whenever our special member functions are called. So for example, here, when we create it, when we copy it, and when we move it, we see that 10 gets printed out each time. In practice, here we have an example where we're adding two elements to our vector in a loop using pushback. We see that the move constructor gets called each time we're adding an element. We see it get called once for 0 and then again for 1. If instead we use emplace back to replace pushback, this will give us in-place construction. So that's our recommendation here. If you're wondering how you should remember that there is an emplace back version of pushback, we have a Clang tidy check that you can use. This is modernize use emplace, and this will let you know that, hey, there is an emplace back version that you can use instead of pushback. This Clang tidy check is also going to work for other iterative containers. It's going to work for stack, queue, deck, forward list, list, and priority queue. There's also kind of a pattern here where there is an emplace version of push and insert functions. So we've summarized a bunch on this slide. This is for dec, forward list, list, stack, queue, and set. There is an emplace version for things like push back, push front, insert after, things like that. All right, let me hand it back to Kathleen.
Thanks. Okay, so now we've looked at many types of sequence containers, and now let's take a look at some more examples with associative containers. First, we'll look at using emplace with maps. Here we have a map M with key type string and value type int, and we're creating a key of string hello and setting the value to 10. So this creates a string and moves it into place. Now let's look at an example with non-trivial types. We'll use our user-defined struct A as the key type and int as the value type. We create a map and assign key A10 to the value of 10. A temporary object is created and then moved into the map. If we instead use emplace, we get in-place construction. So in this case, the key is the non-trivial object. Now let's look at when the value is the non-trivial object. Here we have a map with key type int, value type A, and we're using the subscript operator to assign a key of int 10 to an instance of A initialized with the value of 10. Actually, this code doesn't compile. Struct A actually needs a default constructor for it to compile in this case. Once we add that and look at the output, we can see why, as it creates an object using the constructor that takes an int, and then it creates another object with the default constructor and uses the move assignment operator, and then destroys two objects. Instead, if we use emplace or try emplace, the constructor is only called once and no temporary objects are created. So we can see emplace and try emplace do emplace construction if the value is the non-trivial object. Let's take another look at when the non-trivial object is the key in the map and see if emplace and try emplace behave the same. We'll look at the basic case, not using emplace first, where the key A10 is assigned a value of int10. This creates A and moves an object. If we use emplace instead, only one instance of A is created and destroyed, so no temporary objects were created. Now let's look at try emplace. Does anyone have a guess of what the output will be? Like emplace or like the subscript operator? Well, it's actually the same as the first example using the subscript operator, where the constructor and move constructor are called and two objects are destroyed. So if the key type is a non-trivial object, then only emplace allows in-place construction. There was a paper accepted for C++ 26 that added support for try emplace and the subscript operator that will allow them to behave the same as emplace in this scenario, and they'll do in-place construction. Now let's look at how emplace works for constructors with multiple arguments. We have a struct B that accepts two ints in its constructor. We'll use this in a map with a key type B and value type B. We get a compilation error if we try to pass 4 ints in to create the 2 instances of B, so can't do that. Instead, we have to create 2 instances of B. This calls the constructor and move constructor for both instances of B, so let's see if we can improve on that. Here we'll use piecewise construct with forward as tuple. This only creates the 2 instances of B, so this approach using piecewise construct constructor of pair does in-place construction. If we use try emplace, the key object gets created and moved, but the value object gets created in place. So therefore, it's better to use piecewise construct. Now let's look at when the key already exists in the map. Here we have a map where the key is an int and the value is of type A. We emplace a key 10 with a value of A initialized with 20, and then emplace another value A30 to the same key. There's also an example for try emplace here to compare it to emplace. No extra objects are created, even after emplacing and try emplacing different values. For an existing key, the value type object was not created. However, this is not guaranteed by emplace, but it is guaranteed by try emplace. Next, to take a look at insert or assign, we'll use this struct to see when objects are created in our maps. This is similar to what we used in previous slides, but this time it takes 2 ints in its constructor, and it's a template, so we can name 2 identical types, key and value, as defined at the bottom, so we can see when our key and value objects are created and destroyed. For this code, we can see how these types are used and when the constructors are called for each key or value object. So using these structs, we'll create a map with types key and value. Here we're seeing what happens if we try to insert and assign objects to the same key. So first, the key object k is created. Then the value 2020 object gets created. Then the key value pair gets created, which calls the copy constructor for key and the default constructor for value. Value 2020 is moved into value of the pair, which was inserted into the map. And then lastly, we assign value 3030 to value associated to key 10 in the map. Let's compare to what happens when we use insert or assign. This is doing the same thing and assigning a different value to the same key. The difference is highlighted here. Insert or assign moves the inserted value object instead of using assignment. If you have a function that does both insertion and assignment, use insert or assign instead of the subscript operator. And then I'll pass it back to Prithvi.
Great, thank you. Okay, this next section is on using transparent comparators to avoid extra objects. So this section is going to focus on 4 associative containers: set, map, unordered set, and unordered map. In these examples, we're once again going to be overriding operator new and operator delete. We added that print statement back so that we can detect string creations. The 3 methods that we're going to focus on for all 4 associative containers are count, contains, and find. So kicking off with our set of stewed strings, we can go ahead and reinitialize this set of strings, and then we create this test string. This test string is going to be a C-style chart array, and we want to check count, contains, and find of this test string within our set. What we see in the printed output is that operator new gets called 3 times, once for each of these method calls. So it seems like we're doing a string allocation every single time we call count, contains, or find. First hypothesis here is potentially this is happening because our test string is of a type C-style array, and so it's not matching the stewed string elements that are supposedly in our set. So we can test this hypothesis by trying out what happens if our test string is instead a stewed string. And what we see when we call count, contains, and find is there are no operator new calls. We're not doing any additional string allocations. So if we're not using a const string ref here, the functions count, contains, and find are going to result in these temporary objects being created. Ideally, though, we get this behavior for const char stars for C-style arrays. So if we go back to our broken example here, we see all these string allocations happening because it's converting our C-style chart array test string to a stewed string. If we throw in the stewed less at the top when we initialize our set, we see in the printed output that we no longer get these calls to operator new. And so stewed less here is allowing for these string allocations to no longer take place. Just to do a quick sanity check and make sure we didn't regress our working behavior from before, we can go back to the example where our test string is a stewed string. It does match the type of the elements in our set. And we see here that we don't have any regressions, right? We still don't, we don't have any extra string allocations happening when count, contains, or find are called. And so our recommendation for sets of strings is to use stewed less to get transparent comparison. Transparent comparators allow for comparison to happen without the need to create temporary objects in certain scenarios. They're identified by an is_transparent type def. So here we've copied over the stewed less code from the libc++ code, and we see at the bottom that we have this is_transparent type def. If we're going to take a look at map, our map here has the key type stewed string. We see that we run into the same problem as before. So when our test string doesn't match our key type, we run into this scenario where we have string allocations happening on count, contains, and find. If instead we do the same fix that we did for sets by using stewed less as a transparent comparator, we see that this problem gets solved again. We no longer have those additional string allocations, so we have the same recommendation for maps where the key type is a stewed string. Use stewed less to get transparent comparison. Moving on to unordered sets. Here we have an unordered sets where the elements within the set are going to be of type stewed string. Once again, if our test string is a C-style chart array, we get a bunch of string allocations. If instead we throw in a transparent comparator, we solve the problem, we don't get these string allocations anymore. The transparent comparator that we're using here has 2 pieces. It has myStringHash and equal to. Equal to is straightforward, right? It's checking equality. MyStringHash is a little more interesting, so we've included the implementation here. We see that myStringHash has that is_transparent type def that allows it to be used as a transparent comparator, and it also adds function calls to allow hashing from const char stars, string views, and stewed string. So our recommendation for unordered sets is to use myString hash with equal to get transparent comparison. And then unordered map is going to be similar to unordered set. So here in our unordered map, our key type is once again std string. And when we call count contains and find, when our test string is a C-style chart array, we see the same problem. But when we add myString hash and equal to again, we see that problem gets solved. So the same recommendation applies for unordered maps. Use myString hash and equal to get transparent comparison. We have a summary slide here. This just goes over what we just discussed. Use do less to get transparent comparison for sets and map, and myString hash and equals to get transparent comparison for unordered sets and unordered maps. And with that, I'll hand it off to Kathleen to close out.
Thanks. Okay, so our last topic, moving data to compile time. In our previous examples, we were talking about how to create objects in place to prevent temporary objects from being created at runtime. Instead of creating the object at runtime, we can create it at compile time. Memory for compile time objects is constructed at compile time, which can improve runtime performance. If we have local objects like this, where we have a const string or a vector, the const means we can't modify them. So we can move them to compile time by making them static const expr string view or arrays instead. Let's look at global strings and vectors. If we build using warnings, global constructors, and exit time destructors, we get these errors. This helps identify opportunities for moving global objects to compile time. We can make them const expr string view and array instead and move them to compile time. Oops. So here are the global string and vector again. These global objects are created before main starts. One way we've seen people on our team try to defer global object creation is to make them magic statics. Here we have a static const object being returned by reference in getStir and getVec. The claim flag exit time destructors will also point out magic statics. Magic statics fixes the global constructor issue from the previous slide, but not the exit time destructor error. Sometimes if we move const data structures to compile time, we'll need to make some changes to the usage. For example, here we have a function getVec that returns a const vector reference to a global array. Instead, if we convert global array to a const expr array karray, getVec will need to return a span instead. So the calling code may also have to change. We looked at moving string and vector objects to compile time, but what if we have a user-defined data structure? Here we define a struct sum class that contains 2 strings and an int. We have a const global vector containing objects of this struct, and a function that searches for a string in any of the objects in the vector. This code gets the compiler warning that declaration requires an exit time destructor and a global destructor. Instead, if we make a new vector in getArray and return a reference to it, we don't get a warning. Now the function containStir calls getArray. Absolute no destructor could also be used here to point out this scenario. We can also change our struct to use string view instead of string and array instead of vector, so we can move our user-defined data to compile time using const expr. In our codebase at work, we've seen quite a few instances where we could convert user-defined data structures to compile time. Another scenario we can improve is concatenating strings. In this example, we have 2 const expr string views, and when we concatenate them at runtime, the result will always be the same. In this case, we can use a custom class, myCompileTimeStringJoiner, which we'll look at on the next slide, to do compile time concatenation. So this gives us a compile time concatenated string. And here's the implementation of myCompileTimeStringJoiner. It was copied from the Stack Overflow post, so you can create your own class like this for your own code base. And you can also check out Jason Turner's video from C++ on C last year if you want to learn more about creating compile time strings. Can we move set and map to compile time? There's no standard compliant way to do this. Chromium has defined fixed flat map and fixed flat set that could be used to create compile time set and map. Std flat map and flat set were added to C++23, and they'll be made const expr in C++26. Once they're const expr, then some additional code can be written to create their instances at compile time. Until then, you can consider writing your own simple wrappers. And that's all the topics we're covering today. To recap the key points, we want to have in-place construction without copies or moves. To do this, we can pass non-trivial objects by reference, use view types like string view and span, use in-place constructors for SDL types, use emplace in containers, use transparent comparators, and move data to compile time if possible. You can use Clang tidy checks and warnings to identify potential improvements. And a special thank you to our colleague Chandra, who's helped with this presentation and encouraged us to be here. Also, thank you to the C++ community for all the great articles and videos that made this talk possible. And I just want to point out there are some other talks, other presentations by Microsoft employees at the conference, so if you're interested, please check them out as well. We also have a survey to get feedback, so please use this QR code or the link. As a thank you for filling it out, there's also a raffle to win prizes at the Microsoft booth. Any questions?
Hi, thank you for the great talk. It was really nice to have all of these presented in a short amount of time because a lot of people need to learn some of this. Another trick that I've seen people use on projects where they don't have kind of tidy setup is that they would modify their STL headers and just add explicit to all their copy constructors, and then they get error everywhere where they need to fix things. It's a simple trick, but it can help you if you don't have access to some more modern tools.
Oh, nice.
And I think people should know about this.
Yeah.
Thank you.
Thanks.
Appreciate it.
Hi, nice talk. Can you go back to, I think it was slide 49?
Yes.
Yeah, so in the bottom left-hand corner there, you've got a chunk of code that does emplacement into a vector and eliminates all the superfluous copies. I was wondering, that is somewhat verbose, and perhaps a more condensed way of doing it would be via, for example, to generate n with a back inserter into the vector. Would that create the copies that we're trying to avoid?
I haven't tried that. I'd have to test it out in like a Godbolt session. But yeah, I think that's a good point that this is more verbose. And so a generator approach might be able to like condense it down.
Thanks.
Thank you.
Any other questions?
Oh, and we'll also be posting the slides on Discord. So, yeah.
Amazing. Thanks,
All right,
everyone.
thank you.